Determine the differentiability of a function at the point x equals to a. The function f is differentiable at the point x equals to a if the derivative f prime a is equal to the limit when x approaching a, fx minus fa over x minus a exists at equals to a. Therefore, f prime a is equals to limit when x approaching a from the left for a function fx minus fa over x minus a must equal to the limit when x approaching a from the right for a function fx minus fa over x minus a. If a function is differentiable at a point, then the function is also continuous at that point. However, a function may be continuous at a point but not differentiable. This happens at point where there is no corner or vertical tangent. Look at example below. For both diagram here, at a point x equals to a, there is a corner for the first one, and for the second one there is a vertical tangent from the left and from the right at x equals to a. Hence, f is not differentiable at x equals to a. Example 3. Given fx equals to 2x for x less than 0, x squared for x more than or equal to 0. Is f differentiable at x equal to 0? We can start answering this question by find out what is f prime 0. By applying the formula, f prime 0 is equals to limit when x approaching 0 from the, we find out first one, x from the left, for fx minus f0. The point A here is a equals to 0 over x minus 0. So the limit when x approaching 0 from the left, so 0 from the left here, so this is 0. So you approach 0 from the left, meaning x must less than 0. So the answer is, the function is 2x minus f0, substitute 0 into 2x is 0 over x. Then simplify, limit x approaching 0 from the left for x minus x cancel out to look at 2. So the answer is 2. Now we do the second part. That is, we want to find out what is the limit when x approaching 0 from the right. Means x must more than 0. So f prime 0 is equals to limit when x approaching 0 from the right. Right means x more than 0. We substitute the function is x squared minus 0 squared 0 over x minus 0. So the limit when x approaching 0 from the right for x squared over x, the answer is x. So you substitute 0 into x, the answer is 0. So what is the conclusion? We see that the limit when x approaching 0 from the left for function fx does not equal to the limit when x approaching 0 from the right for the function fx. So we can say that, therefore, f prime 0 does not exist. Okay. So another conclusion we have to make here is, hence f(x) is differentiable or not at x equal to 0. f(x) is not differentiable. Differentiable at the point x equals to 0. So this is the conclusion. Example 4. Determine whether the function f(x) equals to modulus x is differentiable at x equals to 0. So we start answering this question by define what is f(x). f(x) is equals to x if x is more than or equal to 0. Negative x if x less than 0. So for the first one, that is for at less than 0. We find out what is f prime 0. f prime 0 is equals to limit for f(x). For x less than 0, what is f(x)? Negative x minus f0. f0 is 0 over 0, x minus 0. So limit when x approaching 0 from the left. So the limit when x approaching 0 from the left is negative x over x. The answer is negative 1. So final answer is limit for negative 1 when x approaching 0 from the left is negative 1. Okay. Now we do the second part, that is when x more than 0. More than or equal. So f prime 0 is equals to limit when x approaching 0 from the right for the function f(x) minus f0. So what is f(x) when x approaching 0 from the right? The answer is x. So x minus f0, f0 is 0 over x minus 0. So the limit when x approaching 0 from the right is x over x is 1. So the answer is 1. So what is the conclusion that we can make? So the left hand limit is not equal. Like the first example, is not equal to the right hand limit. Okay, so therefore f prime 0 does not exist. So when f prime 0 does not exist, hence f(x) is not differentiable at x equals to 0. Okay, now we move to example 5. Show that the function f(x) equals to x squared plus 3 when at less than or equal 1, and the second one is at plus 3 when x more than 1 is continuous but not differentiable at x equals to 1. So to show that the function is continuous, like you have learned in chapter limit, you have to show that three things. The first one is, what is f1? f1, that is when x equals to 1, f equals to 1 squared plus 3, that is 4. Second one, find out what is the limit when x approaching 1 from the left for a function fx. That is limit when x approaching 1 from the left for a function. Left means less than 1. So the function is x squared plus 3. So the answer is 1 squared plus 3, that is 4. Example 5. Show that fx equals to x squared plus 3 for x less than or equal 1 and x plus 3 for x more than 1 is continuous but does not differentiable at x equals to 1. So we have two parts here. The first part is to show that fx is continuous at a point x equal to 1. So how are you going to show that fx is continuous? So you have to show that you have to consider the point x equals to 1. So find out what is f1. f1, so when x equals to 1, fx equals to 1 plus 4, now 1 plus 3, that is 4. Second one, you have to find out the limit when x approaching 1 from the left. So 1 from the left means, if here is 1, left means at less than 1, the function is x squared plus 3. So the answer is 1 plus 3, that is 4. Find out also the limit when x approaching 1 from the right. So right means more than 1, that is x plus 3. So the answer is also 1 plus 3, that is 4. So we see here that the limit when x approaching 1 from the left for function fx is equal to the limit when x approaching 1 from the right for a function fx, and also equal to f1. When you write this expression, limit of fx when x approaching 1 from the left is equal to limit of fx when x approaching 1 from the right, it only show that the function is it only show that the limit is as is. To show that the function is continuous, you have to equal to f1. Okay, what is f1? f1 equals to 4. So therefore we can say that fx is continuous at point x equals to 1. Okay, now we are going to show that fx is not differentiable at x equal to 1. So we divide into two parts. The first part is for x less than or equal 1. We will see that f prime 1 is equals to limit when x approaching 1 from the left. So we draw the line here. So this is the line x equals to 1. For x less than 1, the function is x squared plus 3. For x more than 1, the function is x plus 3. So substitute here, x squared plus 3 minus f1. So f1 is 1 plus 3, 4 over x minus 1. Simplify, you will get the limit when x approaching 1 from the left for x squared minus 1 over x minus 1. Simplify, you will factorize x minus 1. limit when x approaching 1 from the left for x minus 1 multiply with x plus 1 over x minus 1. Cancel out x minus 1. So the answer is limit when x approaching 1 from the left for x plus 1, that is 2. Okay, so now for x more than 1. For x more than 1, so f prime 1 is equals to limit when x approaching 1 from the right, and the function is x plus 3 minus 1 plus 3, that is 4 over x minus 1. So the answer is limit when x approaching 1 from the right for x minus 1 over x minus 1. So cancel out x minus 1. So limit when x approaching 1 from the right for 1 is equals to 1. So what is the conclusion? We will see that the left side and right side limit does not equal. So we can say that left hand limit does not equal to right hand limit. Therefore, fx is not differentiable at x equals to 1. Okay.